What is reality made of? Is it just what we can see and touch, or is there more to it? It seems like a simple question, but the answer is far from straightforward. We can see, touch, and smell the world around us, experiencing it through our senses. But what happens at the smallest level, far beyond the reach of our senses? What lies beneath the surface? This is where the strange and wondrous world of quantum physics begins, revealing a hidden layer of reality. Quantum physics explores the subatomic realm, a place where the familiar rules of classical physics break down and new rules emerge. Here, particles behave like waves, and uncertainty reigns supreme, challenging our understanding. This realm, invisible to the naked eye, holds the key to understanding the fundamental nature of our universe, unlocking secrets we never imagined. Imagine a tiny grain of sand, something so small yet tangible. Now imagine something a billion times smaller than that, a scale that defies comprehension. You are approaching the quantum scale, where the rules of the universe change. Here, energy, light, and matter all exist as both particles and waves, a duality that defies logic. This duality is just one of the many mind-bending concepts we'll explore, concepts that will challenge your perception. Get ready to question everything you thought you knew about reality, as we dive deeper into this mysterious realm. We are about to embark on a journey into the heart of quantum physics, a realm teeming with wonder and possibility, where the impossible becomes possible. In the quantum world, the building blocks of matter are not solid, well-defined objects. Instead, they exhibit a strange duality, acting like both particles and waves. Imagine a beam of light. Sometimes it acts like a wave bending around obstacles. Other times it acts like a stream of particles carrying energy in discrete packets called photons. This wave-particle duality is a fundamental concept in quantum physics. Electrons, the negatively charged particles orbiting an atom's nucleus, can also behave like waves. They exist in a cloud of probability, their location and momentum uncertain until measured. This inherent uncertainty is not due to limitations in our measurement tools. It is a fundamental property of quantum systems. The act of observation affects the state of a quantum system, collapsing its wave function and forcing it to choose a definite state. The quantum world is a fuzzy, probabilistic realm, a far cry from the deterministic universe described by classical physics. Imagine a coin spinning in the air. It's neither heads nor tails until it lands. In the quantum world, particles exist in a similar state of uncertainty called superposition. A particle in superposition is not in multiple places at once. Instead, it exists in a state of potentiality, a blur of probabilities before measurement. One way to visualize this is to think of a musical note. A single note is made up of many different frequencies or overtones. Similarly, a quantum particle in superposition exists in a combination of different states simultaneously. This concept is crucial for understanding how quantum computers work. Unlike classical computers that store information as bits, 0 or 1, quantum computers use qubits. A qubit, thanks to superposition, can represent 0, 1, or both simultaneously, allowing for exponentially faster computations. Superposition, though counterintuitive, is a cornerstone of quantum physics, shaping the behavior of particles and opening up new avenues for technological advancement. Einstein famously called it spooky action at a distance, the strange phenomenon of quantum entanglement, which puzzled even the greatest minds of his time. Imagine two particles linked in such a way that measuring the state of one instantly determines the state of the other, no matter how far apart they are. This defies our everyday understanding of space and time. This connection is not just a correlation, it's a fundamental aspect of quantum mechanics. It's as if the two particles share a deeper hidden connection that transcends physical space. If you measure one entangled particle and find it spinning up, you instantly know the other particle, even if light years away, must be spinning down. This instantaneous knowledge is truly mind-boggling. This instantaneous connection seems to violate the speed limit of the universe, the speed of light, which is a cornerstone of Einstein's theory of relativity. However, entanglement doesn't actually transmit information faster than light. It merely reveals a pre-existing condition. The correlation between the particles is established at the moment of entanglement, regardless of distance, creating a mysterious bond. Entanglement is one of the most bizarre and intriguing aspects of quantum physics, challenging our understanding of reality. It has profound implications for our understanding of the universe and the potential for developing revolutionary technologies like quantum teleportation. which could change the world as we know it. Section 5. The double-slit experiment, a quantum enigma. One of the most famous and intriguing experiments in quantum physics is the double-slit experiment. It demonstrates the wave-particle duality of light and matter, and highlights the bizarre nature of quantum superposition, a fundamental concept in quantum mechanics. Imagine shining a beam of light at a barrier with two narrow slits, a seemingly simple setup. Behind the barrier is a screen that will capture the light passing through the slits. If light were made of particles, we'd expect to see two bright bands on the screen, corresponding to the two slits, much like throwing marbles through two openings. However, when the experiment is conducted, we observe an interference pattern on the screen, a series of light and dark bands, indicating wave behavior. This pattern is characteristic of waves interfering with each other, creating regions of constructive and destructive interference. Even more surprisingly, the interference pattern persists even when individual particles like electrons are fired at the slits one at a time, defying classical expectations. It's as if each particle interferes with itself, passing through both slits simultaneously, a phenomenon that challenges our understanding of reality. The double-slit experiment beautifully illustrates the paradoxical nature of the quantum world, where particles can exhibit wave-like behavior and exist in a superposition of states, embodying the core mysteries of quantum mechanics. Section 6. Quantum tunneling through walls of impossibility. Imagine throwing a ball at a wall. In the classical world, the ball would bounce back, but in the quantum realm, there's a small chance the ball could tunnel through the wall, appearing on the other side. This is quantum tunneling, a phenomenon where particles can pass through energy barriers that classical physics deems impenetrable. Imagine a particle as a wave. Even though the wave's amplitude is highest on one side of the barrier, there's a small probability that the wave function extends to the other side. This tunneling effect is not just a theoretical curiosity, it has profound implications for various technologies, including transistors, flash memory, and even the nuclear fusion that powers the sun. Quantum tunneling is a stark reminder that the quantum world operates by its own set of rules, defying our everyday intuitions and opening up new realms of possibility. Section 7. Quantum physics in our lives. Quantum physics might seem like an esoteric subject confined to the realm of theoretical physicists. But in reality, it underpins many technologies we use every day. From lasers to smartphones, quantum physics has revolutionized our world. Lasers, for example, rely on the quantum phenomenon of stimulated emission, where photons of light are emitted from excited atoms. This technology is used in everything from barcode scanners to fiber optic communication. Modern electronics, including the transistors that power our computers and smartphones, are based on the principles of quantum mechanics, particularly the behavior of electrons in semiconductors. Medical imaging techniques such as MRI and PET scans also rely on quantum phenomena to visualize the inner workings of the human body. Quantum physics is not just a theoretical framework, it's a fundamental aspect of the universe that has shaped our technological progress and continues to pave the way for future innovations. Section 8. Shaping the future, quantum computing and beyond. Quantum physics is not just about understanding the universe, it's also about harnessing its power to create groundbreaking technologies. One of the most promising fields is quantum computing. Quantum computers leverage superposition and entanglement to perform calculations that are impossible for even the most powerful classical computers. They have the potential to revolutionize fields such as medicine, material science, and artificial intelligence. Another exciting area is quantum cryptography, which uses quantum mechanics to create unbreakable encryption methods, ensuring secure communication in an increasingly interconnected world. Quantum sensors, with their unparalleled sensitivity, hold the promise of revolutionizing medical diagnostics, environmental monitoring, and even our understanding of the human brain. The possibilities offered by quantum physics are as vast as the universe itself. As we delve deeper into the quantum realm, we can expect even more groundbreaking discoveries and innovations that will shape the future of humanity. Section 9. A universe still unfolding. Quantum physics has revolutionized our understanding of the universe, revealing a realm where particles dance in waves, uncertainty reigns supreme, and seemingly impossible connections span vast distances. Yet despite its profound implications, quantum physics remains a field full of mysteries. The interpretation of quantum mechanics is still debated among physicists. What does it truly mean for a particle to be in superposition? How does entanglement actually work? These are questions that continue to challenge our understanding of reality. As we continue to explore the subatomic world, we are likely to encounter even more bizarre and counterintuitive phenomena. Quantum physics reminds us that the universe is far stranger than we can imagine, and our journey of discovery is far from over.